this is lesson 5.5b, or also called lesson 6. We're just doing some more solving word problems involving quadratics. In the previous lesson, we actually did one example, which is a problem involving change. So we had seen that there was someone who wanted to decrease the price and see what the maximum profit would be, as the decrease in price would lead to an increase in sales. And so our strategy there was to let x represent the increases or decreases in the independent variable, and then create two linear equations, so two where there are only x's involved, and then you multiply them together, and that gives you a quadratic relation. Then you could find your vertex and figure out what your maximum sales could be from there. So we did that in the previous video, and that was just one type of problem where you might see a real world problem involving quadratics. Today we're going to focus on another type of real world quadratic problem that involves maximizing surface area. So problems involving maximizing surface area. We're going to do an example together called a four-sided enclosure. So it's a specific type of problem you'll often see. And so the four-sided enclosure, what that really is let's write a definition out for that. It's a square gives you the largest possible area for a given perimeter. And so when we say a four-sided enclosure, what we really mean is four sides to whatever we're building. So the square will give you the largest possible area for a given perimeter, as opposed to a rectangle, for example. Let's do an example to illustrate this occurring. So you're given 120 feet of fencing to create a garden in your backyard. What is the largest possible garden that you can enclose? Start with a sketch. So we always want to start with a sketch, and our problem is going to involve a four-sided enclosure, meaning that this will be our enclosure here. Now we have 120 feet of fencing. So that means that our perimeter is going to be 120. So what that means is we're going to have our width over here, our width over here, our length over here, and our length over here. And so we know that the perimeter of this enclosure is going to be L plus L, so 2L, plus W plus W, so plus 2W. In other words, 2L plus 2W will be equal to 120 feet. Now, the question is asking us, so this is our step one, is writing out just an equation for perimeter. Our step two is really going to be focused on what the question is asking us. The question is asking us, what is the largest possible garden that you can enclose? So the garden is kind of everything that covers the inside of this four-sided enclosure here. In other words, it's your surface area, or your area. So what do we know? We know the area is going to be equal to the length times the width. So we have two equations. We have perimeter is 2L plus 2W equals 120. So this is one of our equations. And then we have A is equal to L times W. Now the problem is we have too many variables here. We have too many variables. We have L and W. We really only want one variable, kind of like x squared. So what we're going to do is we're going to isolate one of the variables. We're going to isolate one of the variables. So this is equation 1, this is equation 2. We're going to isolate, so let's call this step 3. So step 1 was really make the sketch. Step 2 is really make the two equations. Step 3 is isolate one of the variables in 1. So let's choose any variable. Let's isolate L. You could have done W, it doesn't really matter. Let's isolate L in equation 1. So basically it means solve for L in terms of W. So if I were to do that, I'd get 2L plus 2W minus 2W, because I'm sending the 2W to the other side, is equal to 120 minus 2W. And so I get 2L is equal to 120 minus 2W, and then I can divide by 2 on both sides. And so the result would be L is equal to 120. Whoops, like that. Let me erase that and fix that. 120 divided by 2 is 60. 2W divided by 2 is 2W divided by 2 is W minus W. So now you'll notice something interesting. Step 4 is, let's call this equation 3 now. Sub 3 into 2. Here's what you'll notice. So when I do that, I get area is equal to, instead of writing L now, I can replace the L by 60 minus W, because that is L. That's the same thing. So I'm going to replace that by 60 minus W, and then my W in the equation stays there, because my initial equation was A is equal to LW. I just subbed the L I found in step 3 by this. And the reason is, as you can see, is now I only have one variable. This is a quadratic equation in its factored form. You could expand it if you wanted to, but I don't think I need to do that in this case. Let's go see what we need to find. We need to find the largest possible garden that you can enclose. What that means is that we are looking for the maximum area. The maximum area, which, you probably guessed it, for most of these problems is the vertex. So I can perhaps go find the vertex. Now, we can find the vertex in this form over here quite easily. Remember, you can find your zeros. If you find your zeros, then you know the vertex lies in between the two zeros. So for my step 5, I'm going to find my zeros. One of the zeros we know is, well, 0, 0, 0. Because to make this whole thing equal 0, if you put W is equal to 0, then 0 times this will be 0 overall. So one of the zeros is W is equal to 0. So that would be 0, 0. The other 0 is going to be, well, W is equal to 60. Because you can put a 60 in here to make this whole term equal to 0. 0 times 0 would then be, 0 times 60 would then be 0. So to solve for that, let me just show you what we did here. So we did 60 minus W is equal to 0. Just send the W to the other side, or do your inverse operations, and you get 60 is equal to W. So in other words, we have 60, 0. So we found our two zeros, 60 and 0. So what we can do is we can find the midpoint between 0 and 60. So let's do that. We know that to find your vertex, we're going to do the axis of symmetry, which is x is equal to 60 plus 0. And since we're looking for the middle point, it's in between, it's divided by 2. So that's going to be equal to 30. So this is the x value of our axis of symmetry and therefore of our vertex. And so now what we can do is we can plug the this x value into our equation. This is the width at which you have the maximum surface area, in other words. So at a width of 30, you've maximized the surface area for a fence that has 4 sides to it. So let's do sub 30 into equation 4, which is this one over here, into 4. So we get A is equal to 60 minus 30 times 30, which is equal to 30 times 30, which is going to be 900. So this is our vertex basically. What we found is that at a width of 30, we have our maximum area, which is 900. This is our H, this is our K. Based on the fact that our A value would be negative, if you multiply this out, you get negative W squared. We know the parabola opens from the bottom, so we're seeing something kind of like this here. Basically, as you increase the width, so going this way, so let's just say we had our grid here. As you increase the width, the surface area goes up until a maximum point, and eventually it comes back down because it's a parabola here. But this is our maximum surface area up here, which coincides with that 900 value. Therefore, the max area is 900 square feet. We use feet here instead of meters, but that's the process for this maximum enclosure given to you. And so it kind of worked out. If you look at this carefully, the width is 30. So that would be 60, and that means this must be 30 and 30, which coincides to being a square. So we saw how to maximize surface area. We saw how to maximize profit. They all had a very similar approach. You had to have linear equations, and then develop quadratic equations from those linear equations, and then you find your vertex. So if you always follow that approach with these problems, and maybe start with sketches so you can frame the problem, you're more likely than not going to find some kind of solution to it. We're going to take a look at the next question. We won't have time to finish it in this video, but we are going to at least get it started. So the next question is similar, except this time we're going to have a 3-sided enclosure. So a length equal to twice the width gives you the largest possible area for a given perimeter. In a way, I kind of gave you the conclusion before we started. Let's just see if that's actually true. So we're saying that if we have a 3-sided enclosure, if we have a length that's equal to twice the width, that's going to give you the largest area. So we're going to see if that works out. In our previous question, we had said that a square would give us the largest possible area for a given perimeter, and that's what we found. We got 30, 30, 30, 30. Here we're going to see if, when we do our 3-sided enclosure, does this actually support the idea. So our next video, we'll finish this problem up here, and then you can do some more practice with other videos that I post online as suggestions and also in your textbook and in your homework.